Hey everyone, here's our math problem for today. This is a challenging algebra problem. Find all the pairs of integers xy such that x cubed plus y cubed is equal to the quantity x plus y squared. What makes this problem harder is because we want to find all the pairs of integers that can satisfy this equation. If you are just asked to find one pair of those solutions, then it's easier because you can just guess and check. But we want to find all the pairs of integers that can satisfy this equation. You can pause the video and see if you can solve this challenging algebra problem. Now let's solve this problem together. Notice that at the left side, we have here the sum of two cubes, which we can factor as the quantity x plus y times the quantity x squared minus xy plus y squared. And we just copy the right side. Now let's look at different cases here. The first case is when y is equal to negative x. What happens if this y is replaced by negative x? This y replaced by negative x. So clearly, x plus negative x is equal to 0, and x plus negative x at the right side is also equal to 0. So, 0 times any number is 0 at the left side, and the right side is 0, which is an equality. Therefore, if y equals negative x, where x and y are elements of the set of integers, we have infinite solutions here. And so, if we call those numbers as n and its additive inverse, then the ordered pair n comma negative n are solutions to the first case of this problem. Please take note that we are after the integer solutions. Now for the second case, what happens if the sum of x plus y is not equal to 0? This x plus y is not equal to 0. This is what will happen. We can divide both sides of the equation by x plus y. Anyway, the denominator is not 0. So it's valid to divide both sides by a non-zero number. So this one is cancelled out. Then this is raised to the second, this is raised to the 1. This right side becomes x plus y, and the left side becomes x squared minus xy plus y squared. This is a second degree equation, so let's write all the terms at the left side of the equation, and at the right side we have 0. So we subtract x from both sides, we now have here negative x. We subtract y from both sides, we now have here minus y at the left side. Then, there's a common factor x here, so we can factor out the x to arrive at this equation. And let's interchange these two factors to arrive at this form. Notice now that if we let a be equal to 1, b equal to negative of the quantity y plus 1, and c be equal to y squared minus y, that means this a is this one here, this b, negative of the quantity y plus 1, is this part here, and this c, y squared minus y, is this part here, then the given equation at the top would now have this form, ax squared plus bx plus c equals 0. And this is a quadratic equation. Now, since we know that x and y are elements of the set of integers, meaning they are real numbers, then we can only have real solution to this quadratic equation if the discriminant is greater than or equal to 0. And what's the formula for the discriminant? The discriminant is b squared minus 4ac. We would like this to become greater than or equal to 0 to guarantee that the values of x and y that we can get are real numbers, where the set of integers belong to. So, substituting now these values for a, b, and c in order to compute for the determinants, we now have this result. This is our b squared. This is the minus 4ac. So, simplifying, we have here exponent 2, so this negative sign becomes positive. We have y squared plus 2y plus 1. Then distribute negative 4 to get negative 4y squared plus 4y greater than or equal to 0. Then we have here 1y squared and negative 4y squared, which we can simplify to negative 3y squared. 2y plus 4y is 6y, and we copy plus 1 greater than or equal to 0. From here, we can solve for y using the quadratic formula. So solving now for y is equal to negative b, which is the negative of this 6, plus or minus b squared. So 6 squared is 36 minus 4 times a, which is negative 3, times c, which is equal to 1, all over 2 times a, where a is negative 3. Simplifying, 36 plus 12 is 48, and 48 is 16 times 3, and the square root of 16 is 4. So we now have this simplified form. There is a common factor of negative 2 among negative 6, 4 and negative 6, and therefore factoring out this common factor, we now have y equals 3 plus or minus 2 square root of 3 all over 3. So notice that these are the values of y. But we want this equation 3y squared plus 6y plus 1 to be greater than or equal to 0. And therefore, we expect a range of values here. In fact, the decimal representation of 3 minus 2 square root of 3 over 3 is approximately negative 0.15, and 3 plus 2 squared of 3 over 3 is approximately 2.15. If you substitute these values, you'll verify that this equation here at the left will only be greater than or equal to 0 if the values of y are from 3 minus 2 squared of 3 over 3 up to 3 plus 2 squared of 3 over 3, or their corresponding decimal approximation. If you want to check 0, if y is 0, you will have here 1 greater than or equal to 0, which is correct. But let's recall that we want y and x to be elements of the set of integers. We don't want these decimal numbers. And what are the integer values from negative 0.15 up to positive 2.15? Those values are 0, 1, and 2. So these are the 3 possible values of y, so that this equation is greater than or equal to 0 at the same time y is an integer. Now, going back to our main problem, we want to find the integer solutions of x cubed plus y cubed equals the quantity x plus y squared. And we now have here the values for y in the second case. We just need to find what are the values of x that we can pair with these y values. So let's find those x values. First case is if y is equal to 0. So if y equals 0, we now replace this y cubed by 0 cubed, which is 0. Replace this y with 0. And simplifying, we have x cubed equals x squared. And dividing both sides by x squared, we found that x is indeed equal to 1. So the ordered pair 1, 0 is a solution. Now, another possible value here is x equals 0 because 0 cubed is equal to 0 squared. But notice that we said the sum of x plus y should not be equal to 0. If you have 0 for y, 0 for x, then the sum is 0. That is not what you want for case number 2. So when y equals 0, this is one ordered pair solution of our problem. Now let's go to the second case when y is equal to 1. When y is equal to 1, this is what we have. Substitute 1 for y, and we can expand this square binomial to x squared plus 2x plus 1 and copy the left side. Then write everything at the left side and make the right side equal to 0. There is a common factor here of x, and x squared minus x minus 2 is factorable as the quantity x minus 2 times the quantity x plus 1. And therefore, x is equal to 0, x is equal to positive 2, and x is equal to negative 1. That is when y equals 1. So the ordered pairs therefore are 0 and 1 for this. Then we have 2 and 1, and we have negative 1 and 1. Now, what do you notice about this? These are additive inverses that's already covered by our case number 1. Remember, our case number 1 when the sum of x and y is equal to 0. Therefore, we will eliminate this. These ordered pairs are the solutions so far when y equals 0 and y equals 1. So we need to find what are the ordered pair solutions when y equals 2. So when y equals 2, we now have this. X cubed plus 2 cubed equals the quantity x plus 2 squared. Expand the right side and write everything at the left side. The right side equals 0. There is a common factor between these two, that is x squared, and there's a common factor of negative 4 here. And notice that the quantity x minus 1 and the quantity x minus 1 are also common factors that we can factor out. And then that brings us to this difference of 2 squares that can still be factored to the quantity x plus 2 and the quantity x minus 2. And from here, we have x equals positive 1, x equals negative 2, and x equals positive 2. So therefore, we have ordered pair solutions here. X equals 1 and y equals 2. X equals negative 2 and y equals positive 2. Again, notice that the sum of this is 0. So this is already covered in case number 1, so we'll remove this. And the third one is x equals 2 and y is equal to 2. So let's remove the solution that's already covered in first case. So we now have here 1, 2, 3, 4, 5 solutions plus our solution for case number 1. This will now give us all the pairs of integer solutions to the equation x cubed plus y cubed equals the quantity x plus y squared. And what are those solutions? We have a lot of them. Anything that's in the form an integer and its additive inverse are solutions. For example, if you have 5, 5 negative 5 is a solution. If n is, let's say, negative 3, then its additive inverse is positive 3. Negative 3, 3 is also another solution. So there are so many pairs here, plus these 5 specific cases that happens in case number 2 when the sum of x plus y is not equal to 0. At this point, this problem is now solved.